Over the last 10 years, a team of Swedish scientists have been devoted to the development of structural battery composites. In these materials, we use carbon fibers as combined electrode and reinforcement material. Besides the high mechanical performance of carbon fibers, it has recently also been shown that they have very high electrochemical properties. So with these structural batteries, we can actually foresee a route to providing a massless energy storing for carbon fiber composite vehicles, be it cars or aircraft, where the energy storing capability is introduced inside the material. A number of added functionalities have emerged during our work on structural batteries. We illustrate these in the future electric car. Firstly, to make a structural battery composite, we exploit the carbon fibers as negative electrode and reinforcement. By replacing the traditional epoxy matrix with a solid polymer electrolyte and introducing a positive electrode, we turn the carbon fiber reinforced polymer into a structural battery. In another design, we coat individual carbon fibers with a lithium-ion conductive and electrically insulating solid polymer electrolyte, allowing us to bring the positive electrode in contact with the coated fibers. By this approach, we actually turn the coated fibers into cables that can be used to transport data or energy. Thirdly, the team at the Royal Institute of Technology, KTH, has shown that carbon fibers become piezoelectric when lithiated. As a result, the open cell potentially changes when mechanically loaded, and the material can be used for sensing. This mechanism has also been used to harvest energy. With these functions intrinsic to the material, we can make substantial weight savings on the systems level. That is, monofunctional components and devices can be replaced by structures made from the multifunctional composite materials. So carbon fibers has always been designed and made for mechanical performance only. We know very well how the turbostratic graphitic structure looks like for different types of fibers and how it affects the mechanical properties of those fibers. In contrast, almost nothing is known about the carbon fibers microstructure and how it influences the electrochemical properties of the fibers. For us to make better structural battery composites, we seek to answer the question, how does the carbonaceous microstructure of carbon fibers affect multifunctional performance? We perform high-resolution transmission electron microscopy and in situ Raman spectroscopy to explore the influence of the carbonaceous microstructure on the lithiation mechanism and the electrochemical capacity of two types of carbon fibers, intermediate modulus fibers and high modulus fibers. The intermediate modulus fibers T800 and IMS65 have demonstrated very high capacities, whereas the high modulus fiber has low capacity. We show that the low capacity high modulus carbon fiber having highly ordered large crystals integrate lithium ions similar to graphite. However, integration was obstructed by the turbostratic graphitic structure. In contrast, the high capacity intermediate modulus fibers with small and less oriented crystals show the lithiation mechanism reminiscent to disordered carbons. So knowing this about the different carbon fibers, we can actually now move towards multifunctional designs for composites, where we go for high stiffness in one end or high electrochemical performance in the other end.